Welcome to week 9 in review. So the things that we're going to talk about here are, we're in the frequency domain now. We're going to talk about pole placement. We're going to talk about PID control, in particular the I, and also disturbance rejection. And in connection to this, we're going to talk about the final value theorem. So these are the 3 topics that we're going to review right here. So first, for pole placement, let's use the feedback unity loop. So again, as a reminder, feedback unity loop looks like this. Here's our input. Here is our output. So as we've seen, the closed loop transfer function is pk over 1 plus pk. I won't go over how to derive that right now. So let's talk about PD control and an example of pole placement. So, for example, let's suppose that our transfer function for P, sometimes called the plant, looks like 3 plus s over s squared plus minus 9s plus 2. So first question, is this stable? Since this is just a quadratic, we could directly find the roots of the denominator, but we can also just use Routh-Hurwitz. So writing down s squared minus 9s plus 2, the first sequence of Routh-Hurwitz would be 1, 2. The second sequence of Routh-Hurwitz is minus 9, 0. We can stop right here. We don't have to go further because we see that this is minus 9, so the open loop is not stable. So now let's see what happens if we use a P controller. So we use K of S is equal to just K0, then pk over 1 plus pk is equal to K0 times 3 plus s divided by s squared minus 9s plus 2 divided by 1 plus the same thing, K0, 3 plus s divided by s squared minus 9s plus 2. Multiplying out and clearing fractions, we find that this is equal to K0 times 3 plus s divided by s squared minus 9s plus K0s plus 2 plus 3 times K0. So we need to check whether this denominator is stabilizable with a P controller. So again, using Routh-Hurwitz, we find that the first sequence is 1 and 2 plus 3k0. The second sequence is minus 9 plus k0 and then 0. And then the third sequence is derived. It's just going to be 2 plus 3k0. And therefore the conditions we get are that k0 minus 9 has to be greater than or equal to 0, or in other words, k0 must be bigger than 9. And also 2 plus 3k0 has to be greater than 0, or k0 has to be greater than or equal to minus 2/3. One of these conditions implies the other, so we see that indeed with any k0 bigger than 9, the system is stabilizable via a P controller. However, as we see, we do not control independently both coefficients of the denominator, and therefore we cannot place poles in any arbitrary way. So instead, we can use a PD controller. So a PD controller looks like has the P part, but it also has the derivative. So So now let's see what pk over 1 plus pk becomes. It's equal to k0 plus s times k1 times 3 plus s divided by s squared minus 9s plus 2 divided by 1 plus, again, the same thing. Now, clearing fractions, we get that this is equal to k0 plus sk1 times 3 plus s divided by s squared minus 9s plus 2 plus k0 plus sk1 times 3 plus s. Now, we need to do a little bit more work to simplify this. So the denominator is equal to s squared minus 9s plus 2 plus s squared k1 plus 3k1 times s plus k0 times s, that's the s term right there, plus k0 times 3. Putting all these terms together, we have that pk over 1 plus pk is equal to s squared k1 plus 3k1 plus k0 times s plus k0 times 3 divided by s squared times 1 plus k1 plus 3k1 plus k0 minus 9s plus 2 plus k0 times 3. And I'll leave as an exercise for you to check that it is possible to place poles in any way you like. So let's now talk about, and this is true more generally. So the main point, or the main takeaway, is that we add what I'll call derivative terms to the controller in order to be able to do pole placement. So before we move on, maybe it's better to do another example. If p is equal to 1 over s cubed plus 2s squared plus s plus 5, then in order to place poles, we need k of s to have a proportional term, a derivative term, and a second derivative term. Because in that case, pk over 1 plus pk will look like 1 divided by s cubed plus 2 plus k2 s squared plus 1 plus k1s plus 5 plus k0. This is a simpler example than before because the numerator has just degree 1. And we can see that we have independent control over each of the coefficients of the denominator. This means that we can essentially choose the poles of pk over 1 plus pk by choosing the zeros of the denominator. So my favorite example, if we wanted to put them all at -1, then we'd want that polynomial to equal s plus 1 cubed, which is s cubed plus 3s squared plus 3s plus 1. And so we would choose k2 is equal to 1, k1 is equal to 2, and k0 is equal to minus 4, and we would accomplish that. Okay, so now time to get to PID control and disturbance rejection. So recall that for a feedback unity loop, the way that we're talking about disturbance is it entering between the control and the plant. So what's y in this case? Y is equal to the transfer function from r to y times r plus the transfer function from the disturbance d to y times d. And we've computed each one of these. It's pk over 1 plus pk times r plus t over 1 plus pk times d. So disturbance, in order to reject the disturbance, we want to make sure that this contribution is controlled, or ideally 0. So this is what disturbance rejection means. But what does it mean that we want this to be 0? Let me put that in quotes. Well, what we really mean is that, so first of all, we need the system to be stable. And the disturbance rejection part is that we want the steady state contribution of d to y to be 0. In other words, if I look at the portion of y that's due to the disturbance, I want that part to go to 0 in the time domain. That's what steady state means. So steady state again means in the time domain as time goes to infinity. So what are our options here? One option would be to use the inverse Laplace transform. And therefore compute y of t from the Laplace transform, capital Y, and then take the limit as t goes to infinity. But instead, we can use the final value theorem. Final value theorem, which says if the system is stable, in other words, if s times y of s has poles in the left-hand plane, then the limit as t goes to infinity of y of t can actually be computed in the frequency domain, and it's equal to the limit as s goes to 0 of s times y of s. So what this means for us is that we need to compute, we need to design k of s, our control, so that the limit as s goes to 0 of s times the portion of y to which disturbance contributes. So this would be the transfer function from d to y times times d of s. We want this to go to 0 as s goes to 0. We want this to be equal to 0. Okay, so let's do an example again. So let's suppose that p of s is equal to 2 over s squared plus 3s plus 2. Then, and let's suppose that the disturbance in the time domain is a constant. this means that the Laplace transform, so we really mean the constant times the step function, right? Because before 0, everything is 0. This means that the Laplace transform is going to be d0 divided by s. So let's use again our PD control. So suppose we write k of s is equal to k0 plus s times k1, then p over 1 plus pk is going to equal 2 over, if you do the simplification, s squared plus 3 plus k1 times s plus 2 plus k0. So note again that we can do pole placement. But what's the final value theorem tell us? It tells us that the limit as s goes to 0 of s times y of s is equal to, what's y of s? It's 2 over this thing, s squared plus 3 plus k1 s plus 2 plus k0 times d0 over s. After some cancellation, we find that this limit is equal to 2 times d0 divided by 2 plus k0. So we have a non-zero error. And note that exactly like we had in the frequency domain, like in the time domain, the error is proportional to d0. Okay, so now let's introduce the I in the PID control. So we have k of s is equal to, just as before, k0 plus s times k1. That's the proportional and the derivative part, plus the integral part, k2 over s. So now, if I look at p over 1 plus pk, this is equal to 2 divided by s squared plus 3 plus k1 s plus 2 plus k0 plus k2 divided by s, which is equal to 2 times s divided by s cubed plus 3 plus k1 s squared plus 2 plus k0 s plus k2. Some things to notice: the denominator degree increased by 1. This is exactly the translation into the frequency domain of the phenomenon we saw in the time domain, that the dimension of the state increases by 1. Okay, so now let's apply the final value theorem. So assuming that we've done our pole placement correctly and that this thing is stable, remember that is a necessary, we need that for the final value theorem to hold, we find that the limit as s goes to 0 of s times y of s, which is 2 times s divided by s cubed plus this whole denominator times d, which is d0 over s. What happens? The s's cancel, but I have an extra s right here. So this limit is actually equal to 0. And that shows that we can do disturbance rejection with PID control. Extensions and things for you to think about, as you've already done on homework and on the midterm, is what does K need to be when we have a stronger disturbance, when d of t is equal to, say, d1 times t, or d1 times t squared even? Well, the answer comes by looking at the frequency domain. In the frequency domain, d of s would be d1 over s squared, or d1 over s cubed. again, note that I'm being a little careless here, and these should be multiplied by the step function. And that's it for PID control, which means that we've wrapped up pole placement, PID control, disturbance rejection, and final value theorem.